Preparing for a software engineering at New Relic interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a highly available metrics ingestion service? I would separate ingestion from processing. Stateless collectors accept authenticated metrics, validate payloads, apply quotas, and write to a replicated durable log partitioned by account and metric identity. Consumers aggregate and store data asynchronously, allowing independent scaling. I would use acknowledgements only after durable persistence, retry safely with idempotency keys, and isolate noisy tenants. Multi-region routing, health checks, dead letter handling, and dashboards for lag, saturation, and loss would complete the design. While answering, cover ingestion protocols, stateless services, partitioning, buffering, backpressure, replication, idempotency, horizontal scaling, multi-region failure handling, and operational metrics such as throughput, lag, error rate, and dropped data. Question 2. Explain how you would investigate a sudden increase in application latency using observability data. I would first confirm the latency change by endpoint, region, version, and percentile rather than trusting one average. Then I would inspect traces to locate the slow span, correlate it with deployment and dependency metrics, and check CPU, memory, saturation, errors, and database behavior. I would form a narrow hypothesis, reproduce or compare healthy traffic, and mitigate through rollback, capacity, or configuration. Finally, I would document the root cause and add a preventive alert. Make sure to cover symptom validation, golden signals, distributed traces, deployment correlation, dependency analysis, logs, infrastructure metrics, sampling, hypothesis testing, rollback decisions, and communicating impact before implementing a fix. Question 3. What are the main challenges in building a distributed tracing system? Distributed tracing must preserve context across HTTP, queues, threads, and asynchronous boundaries while tolerating missing or malformed headers. Each trace needs stable identifiers, parent relationships, timestamps, service metadata, and sampling decisions. Clock skew means duration interpretation requires care. Storage is expensive, so I would combine head or tail sampling with retention policies and tenant quotas. The system should gracefully display partial traces and connect spans to logs, metrics, deployments, and user-impacting requests. In your answer, discuss context propagation, trace and span identifiers, sampling, clock skew, asynchronous work, storage cost, cardinality, privacy, partial traces, tail-based decisions, and correlation with logs and metrics. Question 4. How would you build a rate limiter for a multi-tenant SaaS platform? I would use a token bucket limiter keyed by tenant, endpoint, and possibly credential. Tokens refill at a configured rate, allowing controlled bursts while enforcing a sustained quota. For multiple instances, I would store counters in a low-latency shared system supporting atomic updates, or partition requests consistently. Responses should include clear retry information. I would monitor rejection rates and hot tenants, and decide fail open or fail closed behavior according to whether availability or protection is more critical. Be sure to mention tenant-specific quotas, token bucket or leaky bucket algorithms, distributed state, atomicity, burst behavior, fairness, retry responses, clock concerns, fail open versus fail closed choices, and monitoring rejected requests. Question 5. How do you prevent high-cardinality attributes from overwhelming an observability platform? High-cardinality fields such as request IDs or unbounded URLs can multiply index size and query cost. I would classify attributes, define budgets, and keep only approved dimensions for metric labels. Raw values could remain in traces or logs with controlled retention, while URLs are normalized and sensitive fields redacted. Ingestion should enforce per-tenant limits, expose rejection or transformation metrics, and provide configuration feedback. The goal is useful drill down without turning every unique value into an indexed time series. Focus on identifying dangerous dimensions, cardinality budgets, allo lists, aggregation boundaries, normalization, per-tenant controls, storage indexing costs, query performance, user feedback, and preserving useful debugging context without accepting unlimited labels. Question 6. Describe a safe strategy for evolving a public API without breaking existing customers. I prefer additive evolution. Introduce optional fields, preserve existing meanings, and make clients tolerate unknown response fields. For incompatible behavior, I would version the endpoint or media type and publish a deprecation timeline. Contract tests protect representative customers, while telemetry identifies remaining old usage. I would provide migration examples, dual read or dual write transitions when necessary, and staged rollout with rollback controls. Compatibility is a product promise, so it needs monitoring, ownership, and explicit communication. Cover backward compatibility, additive changes, versioning, schema validation, deprecation windows, contract tests, telemetry, migration documentation, feature flags, rollout stages, and handling unknown fields or older clients. Question 7. How would you design a durable event processing pipeline that handles duplicate messages? I would assume at least once delivery and make each consumer idempotent. Events receive stable IDs, and the consumer records processing state or uses an atomic upsert so retries cannot duplicate the business effect. Offsets should advance only after durable work completes. Transient failures retry with backoff. Poison messages go to a monitored dead letter queue. I would define ordering per entity rather than globally, retain events for replay, and avoid promising exactly once behavior unless every boundary supports it. In your answer, discuss at least once delivery, idempotent consumers, event keys, durable offsets, retries, dead letter queues, ordering scope, replayability, schema evolution, and the limits of claiming exactly once processing. Question 8. What is the difference between strong and eventual consistency, and when would you choose each? Strong consistency means reads reflect the latest successful write according to a defined ordering. Eventual consistency allows temporary divergence before replicas converge. I would choose strong consistency for billing, access control, and configuration where stale data causes incorrect decisions. Eventual consistency fits dashboards, analytics, and replicated caches where availability and latency matter more. The decision should be explicit. Define acceptable staleness, expose it to users when relevant, and add reconciliation for conflicting or delayed updates. Make sure to explain visibility guarantees, latency, availability, partition tolerance, user expectations, read after write behavior, conflict resolution, and examples such as billing, dashboards, configuration, and analytical data. Question 9. How would you optimize a slow query in a large time series data store? I would begin with the query plan and production traces, checking time range, filters, grouping dimensions, scanned partitions, and returned series. Then I would push predicates and aggregation into storage, align partitioning with time and tenant access, and use rollups for older data. Cardinality limits, query cancellation, per-tenant budgets, and caching protect the system. I would benchmark realistic workloads before and after changes, because an optimization that helps one query may harm ingestion or other tenants. Discuss query shape, time range limits, partition and index selection, aggregation pushdown, downsampling, hot and cold tiers, cardinality, query plans, caching, cancellation, resource isolation, and measuring improvements against representative workloads. Question 10. How would you implement reliable retry behavior for calls between microservices? Retries help only with transient failures and can worsen overload. I would propagate a deadline, retry a small bounded number of safe operations using exponential backoff and jitter, and require idempotency keys for mutations. Circuit breakers and retry budgets prevent cascading traffic, while callers stop when the deadline expires. I would not retry validation errors or saturated dependencies blindly. Metrics should distinguish original failures, retries, exhausted budgets, and downstream recovery so tuning is evidence-based. Cover transient versus permanent failures, exponential backoff with jitter, retry budgets, ID impotency, deadlines, circuit breakers, bounded attempts, observability, thundering herd prevention, and avoiding retries for overloaded downstream services. Question 11. Tell me about a time you improved the reliability of a production service. In one service, intermittent timeouts came from an unbounded connection pool during traffic spikes. I confirmed the pattern through saturation metrics and traces, then added bounded pooling, request deadlines, load tests, and an alert on queue wait time. We rolled out gradually and reduced timeout errors by roughly 80%. I also wrote a runbook and reviewed capacity assumptions with the owning team. The lasting improvement was treating resource limits as explicit reliability controls, not hidden defaults. Be ready to structure the story with context, measurable impact, diagnosis, prioritized actions, trade-offs, stakeholder communication, validation, incident learning, and a lasting prevention mechanism such as tests, alerts, or runbooks. Question 12. How would you test a distributed system that processes telemetry data? I would test in layers. Unit tests cover parsing, aggregation, and edge cases. Contract tests verify protocols and schemas between agents, collectors, and storage. Integration tests exercise retries, duplicates, ordering, and partial failures. Load and soak tests use realistic tenant distributions and cardinality, while fault injection kills consumers, delays dependencies, and fills queues. I would assert invariants such as no data amplification, bounded lag, and correct totals, then replay sanitized production samples before releases. Focus on unit and contract tests, deterministic integration environments, property-based validation, failure injection, load and soak testing, replayed production-shaped data, correctness invariants, observability assertions, and testing upgrades or schema changes. Question 13. What concurrency issues can arise in a Go service, and how do you prevent them? Common failures include unsynchronized shared state, Go routine leaks, deadlocks, and workers that ignore cancellation. I keep ownership clear. Channels communicate work, while mutexes protect narrowly scoped state. Every Go routine receives a cancellation path, and worker pools are bounded to provide backpressure. I run the race detector, stress tests, and leak checks, and avoid copying synchronization primitives accidentally. The design should make shutdown, error propagation, and resource limits explicit rather than relying on convention. Mention data races, Go routine leaks, channel ownership, mutex scope, deadlocks, cancellation, bounded workers, shared state, race detection, structured concurrency, and choosing channels or locks based on the communication pattern. Question 14. How would you protect sensitive customer data in an observability product? I would classify telemetry before deciding what to collect, minimize sensitive fields, and provide configurable redaction at the edge. Transport uses modern TLS, storage uses encryption with managed key controls, and authorization enforces tenant isolation and least privilege. Retention and deletion policies should be auditable, with access logs and periodic reviews. Secrets never belong in attributes or logs. I would also threat model ingestion, query, export, and support workflows because leakage often occurs outside core storage. Cover data classification, encryption in transit and at rest, tenant isolation, least privilege, redaction, retention controls, audit logs, secret management, access reviews, regional requirements, and avoiding sensitive data in telemetry by default. Question 15. How do you decide whether a new feature should be synchronous or asynchronous? I choose synchronous processing when the work is short, bounded, and the user needs an immediate result, such as validating a request. I choose asynchronous processing for long-running, bursty, or failure-prone work such as backfills or report generation. The asynchronous API should return a job identifier, expose status, support retries and cancellation, and make completion observable. Synchronous paths still need deadlines and protection. The key trade-off is simpler interaction versus resilience and independent scaling. Discuss user latency expectations, work duration, reliability, consistency, retries, feedback mechanisms, queue capacity, operational complexity, cancellation, idempotency, and when immediate confirmation is more valuable than eventual completion. Question 16. How would you roll out a risky change to a critical production service? I would first map dependencies, define success and rollback thresholds, and make the change backward compatible. I would deploy Dark, enable it for internal traffic, then use a small canary cohort before expanding by region or tenant. Guardrails include error rate, latency percentiles, saturation, data correctness, and customer impact. Feature flags separate deployment from activation, while automated rollback limits exposure. I would keep an incident owner available and record decisions, results, and follow-up actions. In your answer, include dependency mapping, backward compatible migrations, feature flags, canaries, guardrail metrics, staged exposure, automated rollback, runbooks, ownership, communication, and separating deployment from activation. Question 17. Explain the role of OpenTelemetry in a modern observability architecture. OpenTelemetry provides vendor-neutral APIs, SDKs, instrumentation, semantic conventions, and collectors for generating and transporting traces, metrics, and logs. I can instrument an application once, propagate context across services, and route data through collectors to one or more backends. Collectors also handle batching, filtering, enrichment, and export reliability. I still need backend-specific decisions around indexing, retention, and querying. The main benefit is portability without sacrificing consistent correlation and instrumentation standards. Be sure to cover vendor-neutral APIs and SDKs, traces, metrics, logs, context propagation, collectors, exporters, semantic conventions, instrumentation strategy, sampling, and separating telemetry generation from backend storage. Question 18. How would you diagnose memory growth in a long-running service? I would compare heap usage, allocation rate, garbage collection activity, traffic, queue depth, and restart history. A heap profile can reveal retained objects, while allocation profiles show churn that may create pressure without a leak. I would inspect caches, listeners, go routines, buffers, and unbounded queues, then reproduce the pattern under realistic load. Short-term mitigation might reduce traffic or restart safely, but the fix requires ownership analysis and a long-duration test proving memory returns to a stable baseline. Discuss distinguishing leaks from legitimate growth, heap and allocation profiles, garbage collection, caches, queues, retained references, traffic correlation, load reproduction, container limits, safe mitigation, and validating fixes over time. Question 19. How do you prioritize engineering work when reliability, customer features, and technical debt compete? I frame each option using customer impact, probability and severity of failure, effort, and strategic value. Reliability work gets priority when it threatens commitments, consumes an error budget, or blocks safe growth. I split large debt into incremental improvements and pair it with feature delivery when possible. I bring evidence from incidents, support issues, and usage data, then make trade-offs explicit with stakeholders. A written decision and review date prevent urgent work from becoming permanent neglect. Focus on customer and business impact, risk, urgency, evidence, reliability budgets, dependencies, opportunity cost, incremental delivery, stakeholder alignment, and making trade-offs visible rather than optimizing for the loudest request. Question 20. Design a multi-tenant alerting system that avoids notification storms. I would evaluate conditions from durable time series data, then group related incidents by tenant, service, and failure signature. Deduplication keys, hysteresis, cooldowns, and dependency-aware suppression prevent repeated notifications and storms. Each tenant receives isolated quotas and configurable routing, escalation, and quiet periods. Delivery uses an outbox with retries and idempotent provider calls. Every alert should explain its evidence and state transition. I would measure notification volume, acknowledgement time, false positives, and missed incidents. Cover alert evaluation, tenant isolation, deduplication, grouping, correlation, hysteresis, cooldowns, notification budgets, escalation, delivery retries, user configuration, explainability, and measuring false positives, recovery time, and alert volume. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.